Welcome to this demonstration. Be sure to check out the video description for a link to the companion document, and that will contain multiple different resources like a link to this graph, inputs, and a transcript, all of which to help you follow along or take these things and use them as you like in other applications. Now this whole graph is set up with a defined toolkit function from the start. That might be called a parent function or a reference function depending on your course. But these are functions like x squared, x cubed, square root of x, cube root of x, absolute value of x, 1 over x, or just f of x equals x. All of these have different names. Essentially, there are building blocks for function behavior. I'm going to completely focus on this x squared toolkit function until I get down to Symmetry, where I will talk about some other toolkit functions as well. Now in this demonstration, I'm going to show you how I created these things along with some of the nuance to that process. This first couple of inputs is just to define the function and plot a few points. This table is brought up just when I have my cursor on that function, using edit list and create table. You can tell that this is the way I did it because it doesn't have a subscript. If you add a table using the add item button, it will use X subscript 1, 2, 3, or so on. I like this method of plotting points. It will always plot from -2 to 2 in increments of 1. And I'm just going to leave that as sort of 5 key points on this graph. For most graphs, that's going to work really well. Some graphs like square root, here I just type sqrt to bring up that square root, or you can find it here. Anytime it's an even index root, we'll get some of those that are undefined, but that's perfectly fine. I think it's nice to leave those in and show that we have some restrictions on our domain. Now diving into this first folder, this is our transformations. I've set this up using 3 inputs, and I just typed in this function and then clicked the button to add the sliders, and then I made some changes to those sliders. You can restrict these in certain ways. For example, H and K being the horizontal and vertical shifts, you may want to limit those to a step of 1, which will help keep us on those specific whole number vertices. And then A, that one might be okay if it's a decimal because we might want a compression factor or we might want a vertical stretch factor. So this is going to be our vertical compressions, doing numbers that are less than 1, or I should say an absolute value less than 1 because we could get negative decimals. Or it'll be a stretch when we go beyond 1 or beyond -1. I've chosen to leave off a factor on the input, but you could add B, capital B, however you want to do that, with parentheses around x minus h, and you could handle that as well. And there it might be helpful just to note that going to large values for B tends to compress it horizontally, stretch it vertically. Now it won't compress and stretch at the same factor. Here we'll compress, for example, if I set B to 2, I'll compress my inputs to be half of that and move the inputs into, for example, from 2 into 1. It might be helpful to see that with A set to 1. So here you can see these 2 points. Let's align all of these to 0. And there we can see it a lot better, is with a B of 2, we actually have half the horizontal spread. So that's a compression of 1/2, compression factor of 1/2, multiplying by 1/2, dividing by 2. It's hard to make sure the wording is always precise, so it's better to just be clearer. Now, that would actually look the same as a vertical stretch. So if you look, what happened is the points -2,4 and +2,4 shifted in. And so we can kind of see that, but wait a minute, what happened to these down here? Now, actually, it ends up being the same as if we were to stretch it up times 4. And that's because really this b could be factored out of the function. That's inputting a b times x squared, and squaring b is just 4 on the outside. So 2 on the inside is the same as 4 on the outside. Ultimately, long story short, we really don't need b for most applications. Most of the time you can translate a horizontal stretcher compression into a vertical stretcher compression and make it work just fine. Now, where did okay, there's my function. I was wondering where that went. Right now they're aligned. Now, the other thing I can do is I can, just make this whole thing movable. And a nice way to do that, or draggable, I should say. A nice way to do that is just plot the point HK. That wasn't in my original graph, but if you wanted to add that, it would add that in as a draggable point. Might make sense to change this to match. And you can also, once you're in those settings, you can see the drag settings. If you only want it to go vertical or horizontal, you can do that. And that was just using edit list, clicking on the color next to the input to bring up all those options. For some applications, it might be helpful to add a label. For example, for this parabola, I have a vertex. If I change to a different toolkit function, that won't necessarily be the same. Now the vertex is at HK, and I'm going to show you one other little function of Desmos while we're at it. I can turn these variables into actual numbers. What I need to do is start by changing it to a math type or mathematically defined phrase, and that's with the backticks on either side of it. It's the same button that makes the tilde to make those backticks. And now all it did was it made it look fancier. It kind of has this script look like you see in math textbooks and proofs. To make it evaluate h and k, you need a $sign and braces around each separate variable. So right around the h, I'm going to do the squiggly lines that are called braces. And that's not it. Let's try that again. There we go. It's the same button as the brackets, but with a shift. And then I put a $sign in front of it, and that's basically saying evaluate this variable. The backticks tell it that it's kind of a mathematical phrase, and the $sign with the braces gives you that specific evaluated point. Probably more than you asked for, but who knows, that could come in handy at some point. Of course, vertex isn't going to apply if I change this to different types of functions like a square root function. Now we can look at the next folder, which is mapping the transformations. I think I'll leave everything just how I have it and just collapse that folder. We're looking at the map transformations folder now, and we see there's not much to it. I'll toggle on this whole thing. What you see is a movable point. That's the one with the shading. And it kind of happened to be in a weird spot there, but it should be on the original toolkit function. And it's one that we can drag around. Okay, so that one, I just actually typed a f of a. So I'm saying let's just define a new point on this line. X values a, and then we'll evaluate it. It is draggable left, right. I can't really do all direction drag because y is tied to x. So I should leave that the way it is. I think that was the default setting, but I did change it to an x because I wanted it to be a very different looking point. And now I apply the translation left and right. So if h is positive, it's going to add, move it right. If h is negative, it's going to subtract. So I don't need to do that whole flip thing that I did like back here. We just do that once to make sure that h is positive for right and negative for left. And after that, we don't have to keep using this x minus h thing. Oftentimes we'll call these roots because it's sort of like h is the number that would make that 0. So if you put in an h minus h is 0. That's the only time we have the negative. Down here, we don't need it anymore. So we're going to take our original point A, shift it left or right, and evaluate it at that point. And now we get the corresponding point on the transformed graph. And I can actually leave that, come back here, and do all kinds of adjustments that I want to do, and it should be fine. So see that red X is staying in that corresponding place, even if I flip it around, upside down, stretch it. So there we can see that that point, exactly where it got shifted to and from, depending on where I started. That process is called mapping, where you're really looking at where did this start and where did this end, and the process in between would be those transformations to get there. Now the last folder here, I'll turn off my transformations. I can turn off both of those folders, and you can turn this one on. It really just has two pieces to it. So you'll see two dotted lines, a red one and a purple one. The red one is showing us what happens when we reflect it about the y-axis. Now in this case, I'll shut the other one off. In this case, we get the same exact looking graph. And that's because it was symmetric around that center line. In other words, it's mirrored. It was already mirrored. This just checks to see if we get that mirroring. Because it has that symmetry, we'll call it an even function. You'll get that for x squared. X to the fourth is going to work as well. And some others. I think absolute values may be the other notable one. Now, the next type of symmetry that I have here is not symmetry about the x-axis. We don't talk about that too much with functions because we can't have points above and below the x-axis. That wouldn't be a function anymore. So I originally had that and got rid of it because I realized there's no function that's going to have that symmetry about the x-axis. The last one that we have here is symmetry about the origin, which is essentially a left, right, and a vertical flip. So you flip the input and the output. That's 180-degree rotation. And I was waiting to type this in because I wanted to do x cubed, which you can see does not have only the y-axis symmetry. That one isolated out doesn't work, but this one does. So if we flip it that way and that way, left, right, and up, down, essentially it's like rotating it 180 degrees, halfway around, and all the way around and as many times around as we need to. That is called an odd function. We'll get it with odd powers. We'll also get it if we have a sum of odd powers. So x to the fifth plus x to the third plus x. They're all odd powers, so it works. And if we made them all even, such as x to the fourth plus x squared, and then just got rid of that piece at the end, we go back to all even powers means even symmetry.